But I now turn to the main event of the evening, and I'm sorry we've cut it a bit short. I've been gone on a bit. I could go on for very much longer about Hugh Durrant-Whyte. As you know, he's the New South Wales Chief Scientist and Engineer, Natural Resources Commissioner. And I think it's probably fair to say that New South Wales is incredibly lucky to have a Chief Scientist with almost a renaissance range of achievements and global reach. Just to pick out one or two, from 2016 to 18, Hugh was Chief Scientific Advisor to the UK Ministry of Defence. On two separate occasions, he was Professor and ARC Federation Fellow at the University of Sydney. He was CEO of the National ICT Australia, Director of the ARC Centre of Excellence for Autonomous Systems, and of the Australian Centre for Field Robotics. His leadership in these fields of robotics over many years is well attested, and if I were to read out the lists of honours he's received and societies of which he's a member, it would take us too long. But I must say I was very struck by the fact, Hugh, that you've also co-founded 3 successful startup companies, a renaissance figure indeed. So he will talk to us tonight about engineering the future. Thank you very much.
It's great to be here this evening. It's lovely to be here actually in a library as well, looking at all the books and things like that. My library at home is not quite as big, but it's getting there, I think it's fair to say. I think the first thing I'd like to do is to congratulate Susan. Susan and I have known each other many, many years, and she has done an absolutely astonishing job with the fellows of the Royal Society here in New South Wales and the whole organisation. Not only has she extracted money from me, but she's genuinely taken it in a new direction, many new directions, and really, I think, laid the foundations for what it could be in the future. Actually, today I was reading the proceedings of the New South Wales Royal Society, dated 1890, if you're interested, about people reading papers to the Society about statistics, about livestock, about growing things, about all the contributions they were making to the state, about all the new things that we were doing down here. And I think it would be great to see the new Royal Society do these things into the future. So really, thank you so much, Susan, for putting it where it is today. So, if there's one thing you should know about me, I'm an engineer. And it's not because I happen to qualify as an engineer. I've got engineering in my blood, actually. The things that make me most proud in life are the things that I have converted from mathematics into things that actually do things, whether they be cranes on the Harbour Bridge, or whether they be robots in the Pilbara or anything like that, or the fact that my hobby is building houses at home. So I'm always getting in there and really trying to make things out of what I know and what I want to do. It's in my blood. I am an engineer. And I've been very, very fortunate in my career, and I think many of you here will have as well, to actually have been through arguably one of the biggest upheavals in technology and engineering there has ever been in the last 50 years. I remember, actually it was at school, I had my first email address, believe it or not, in the 1970s. So it's, some of these things take a little while to evolve, but my first job, and I'll come to that in a little bit, I remember programming computers using punch cards. And I still own a slide rule and know how to use it as well, which I can impress my grandchildren with one day. So things have moved on astonishingly. You know, I look at what's happening today. We are building computer chips with over 2 trillion transistors, capable of processing speeds in exaflops, an exaflop being 10 to the power of 15. And a whole range of new algorithms and technologies that really have completely changed the planet in so many different ways. I do feel privileged though, because I have kind of had a front seat throughout this. I originally was a nuclear engineer, you know, and I thought at that time at least nuclear was where things were going to happen. I have to say at the time though, we had 3 Mile Island, and the whole industry kind of got a hole in it, although what I'm learning now is that my old skill sets in this area are actually marketable, as everyone tries to look at nuclear as the new future. And again, I might say a little bit about that later on as well. And I converted to doing robotics. And it was a time when actually they hadn't even had a conference in robotics when I started. I actually went to the very first ever conference on robotics. And for all you budding academics out there, I can tell you it's much easier to make progress in a field where there isn't anyone. all right, than there is when it's full of people. And so it was a wonderful time for people like me, where we started doing things like inventing autonomy, using AI for the first time, actually trying to build embodied systems, build robots that really did things in different kinds of ways. It was terrifically exciting. And it also is driven by a lot by the technology that's been out there. So, you know, we started in days, or I started in days when it took us 4 hours on a mainframe computer to process one computer vision image, all right? And now, of course, we do that instantly, every time, everywhere on your phone even. And things have changed like that. And sensing technology, we used to have very, very primitive sensing technology, but now computer vision, lasers, radars, everything else you can buy and put in your phone, navigation systems, GPS. It's untold the number of things that have really impacted the field that I started in a long, long time ago. And it's also interesting, I guess, the way that we now just treat it as completely normal. It just isn't a surprise anymore that we can do these sorts of things, and I think that itself is interesting. So I was asked a couple of years ago to think about the future of engineering. What would it like? What's it going to be like? We've had a tumultuous and really interesting last 40 years. What's it going to be in the next 40 years? Where will we be in all these different areas? And part of this was also setting up, I think, our 20-year R&D roadmap, which we developed for the New South Wales government. Where are the places that we need to be building and investing in and things like that? But also part of it was really taking what we've got now and trying to understand, you know, where these technologies would go in the future. And I think there are 4 areas for us that really stood out for lots of different reasons. First one, of course, is digital. And I'll come to it in a few minutes, but I think it's fair to say I think we've only just begun the digital revolution. We are nowhere near the capacity that we will be at points in the future. But the other one that has really taken me by surprise, and anyone who knows me now knows that I spend half my time reading books on this kind of stuff, is biology. I think biology, and now I'm actually going to annoy a few people calling it engineering biology, all right, is going to be bigger than digital. It is going to be utterly transformational in so many different ways, and I will elucidate some of that as I go along. And I think, you know, it's almost to the ilk now where I'm trying to explain to deans of engineering, really, you know, you need to be teaching digital and biology, because that's where the future is, you know, and those are the sorts of things that we all need to be interested in and concerned about. The 4th area is materials. Again, I come from a generation where, you know, material science was getting a piece of metal and bending it in interesting ways and seeing what happened. And now, you know, just to give you one example, and I'll talk about more of these later on, I was reviewing a project in the US recently for a very, very small nuclear reactor, what's called a microreactor, so smaller than this computer, okay? And it used really interesting composite materials which morphed and changed in order to control the system, all right? So these materials now are really unbelievably sophisticated, the kinds of things that you can do with them in so many different ways. And again, I'll unpack that a little bit as I go along. And the last area, which I think is of critical importance also to Australia, is energy. We are having an energy revolution at the moment. I've got to be honest, it's all a bit worrying. I am also a net zero commissioner amongst all my other roles, and I'm trying to hold the government to account over meeting its targets for the energy transition. And I don't think it's any news to anyone in this room that there is no chance on the planet that we will meet them at this point. Because the energy transition is much more complex than I think people realize. Having said that, the technology space in this area is profound. There are so many companies doing so many interesting things and researchers in everything from chemistry to electronics to materials to just the whole way that things work and the whole way that we behave as a community. So I also think that that's an area where, again, engineering will really make a big difference into the future. And then above all of those is the fact that all of these things mesh together, all right? They come together in really interesting ways, profound ways, I think, that will ultimately change everything that we look at and everything that we do. So let me rehearse some of that, and I'm going to talk about all of those different components as I go along. Let me first sort of say something about digital technologies. I do think it's amazing the way things have gone in the future. We're here with our mobile phones, at least you guys are. As some of you know, I don't own a smartphone for other reasons. But I also look at all the compute power we have every day of the week to do everything. The way that our whole civilization has become to depend on these sorts of things. And I also look at technologies like AI, and I often like to point out to people at this point, AI is kind of not a new thing. I mean, not only did I read my first book on it well over 40 years ago now, but actually I went along about 5 years ago to the 60th anniversary of AI that was held at MIT. So we all thought we were doing the right thing then. Of course, we've been through many, many hype cycles. I remember when I was first a graduate student, everybody wanted to be a knowledge engineer. Okay? We don't even know what one is anymore because it's just disappeared on the horizon. But nevertheless, those sorts of things where we develop algorithms and we develop systems and the way that we've applied digital technology has really transformed everything. One of my jobs, again, you'll realize that I have more jobs than most people, is I work 1 day a week for Rio Tinto. And I've been doing this for about 30 years. And I run their automation program, how to automate the Pilbara and all their other mines. And the big thing at the moment is how we apply machine learning techniques and data techniques to doing things like geological exploration, to controlling processes, to managing systems, to the whole sort of thing. The use of algorithms and digital technology in all of these areas is just tremendous. And I could say the same thing about agriculture and other areas as well. So I think all of these things is really, really interesting and important. Having said that, I think we also need to understand we have just started. You know, people think that we are about to head towards general artificial intelligence. It is not going to happen. Do not worry. Go back to sleep. Okay? It is, you know, arguably even on the wrong road, and I'd even put money on it that I suspect the large language model thing will disappear off a cliff before the end of the year, actually. But there are nevertheless fantastic things that are happening with machine learning and AI. Designing proteins and new drugs, new materials and buildings. Whole ranges of different things have really been opened up by this kind of technology. At the same time, I think something that people talk about but kind of underestimate is the way processing power has changed. I was trying to get some numbers out there, but the scale of what's happening at the moment is truly amazing. One of the most powerful processors in existence is now on a smartphone, 3 nanometer technology, 10 to the power 12 transistors. I mean, it's just uncountable, right? And people manufacture those, in series production, and everyone can have one, and they're virtually free. And memory is completely free. Do you ever remember when you had floppy disks and things like that, and you really counted how many things you did? The whole thing has changed. And that itself has opened up huge numbers of ideas and applications to everybody. And again, we're still at the basis. I will come to quantum in a minute, but I mean, I've been doing some work on biological computers. 1 cubic centimeter of DNA will store 10 to the 19 bytes, which is more information than humanity has created ever. All right, in 1 cubic centimeter. We can get proteins to basically do calculation. We glue them onto silicon now, and we can get them to do computation as well. It's kind of like new things are happening where these different pieces are all coming together. And quantum, again, for people who know me a little bit, I have lots of quantum books stacked up. I like to know what I'm doing in all these different areas. And it's interesting to see the investment and the great companies that we built in New South Wales around quantum computing. There are 3 or 4 really great companies: Dirac, Silicon Quantum Computing, Quantum Brilliance, Q Control, and so on, who together, incidentally, have raised well over $500 million in the last couple of years. It's that kind of investment that's going on. And we're still at the beginning of that journey. Quantum computers will be good for lots of interesting things. They'll be good, for example, for simulating quantum systems, so building batteries, new materials, new proteins, and so on. But at the same time, they won't be good for everything. All right? It turns out quantum computing is not good at doing things like AI, because it's not very good at reading in data, and it's not very good at doing matrix multiplications and useful other things like that. So again, this is a kind of technology that offers and will open many, many doors in the next couple of years, but it'll be interesting to see how we basically go and apply it. I think there are also challenges in the digital area. If there's one big one that is getting scarier and scarier, it's things like cyber. The way that we're being hit in this area. I think there are opportunities, though, to real mathematically prove that computers can never be hacked. This type of thing. So, real interesting technology, which again, universities in New South Wales are at the forefront of doing. And this idea where I think we're now beyond what a single human or even team of humans can do with a computer. How do we actually make that whole scaling thing happen? So digital technology is going to really change things and transform things even more than it does. And I will come back to that where it intersects with all these other disciplines. Now, if you think I'm excited about digital, you should see how excited I am about biology at the moment. You can't have a conversation with me without me talking about non-coding RNA and a whole range of other things that are going on. I've been banging on about this for a couple of years. I think we'll come to a little bit later on. You know, things like AlphaFold. 2 computer scientists won the Nobel Prize in medicine last year. All right, that is amazing. All right, that sort of thing would never have been even conceived in the past. And I think the whole idea where you can now start thinking about changing biology from what used to be something you did with a white coat in a lab into something you do on a computer where you design and you manufacture things has completely changed stuff. I often go and visit at Macquarie University the ARC Centre of Excellence in Synthetic Biology. This is basically a whole centre, a whole group of hundreds of people who are out there designing and manufacturing new organisms. All right, new proteins, new types of ways you modify yeast to produce fuels, to do a whole range of different things. The opportunities also for really thinking about how you use proteins in different ways, not just to, I don't know, solve a medical problem or a drug problem, but to begin to make structures, to even make machines out of this sort of stuff. The opportunities in biology are quite staggering relative to kind of where we are. We are really just at the beginning, and I like to, again, annoy my biology colleagues by saying the real transformation that's happened in biology in the last 5 to 10 years is the fact that now it has become engineering. All right? It really is about designing and manufacturing things in a different kind of way. And I like to put a lot of provocative questions out there, you know, around biology to the biologists, but also trying to bring together the mathematicians and the engineers together. Is there a mathematics of biology? Is there a mathematics of life? There is an ARC centre that's been established in the mathematics of life down at Melbourne, okay, with collaborators up here and everything else. And can you use that mathematics to really predict, to design, build and predict, which is what engineering is all about, right? And actually put these sorts of things together. A traditional biologist would say, no, biology is not like that. But things are changing. People have now won Nobel Prizes for this. So it is genuinely at the cusp of doing something different. I also like to think of biology in terms of building mechanical machines, electrical machines, a whole range of other sorts of things. And genuinely, can we use it for actual real discovery of drugs and therapeutics and things like that in a predictive manner rather than just running a whole bunch of experiments. I also like to think about, and I mentioned this earlier, about the use of biology for computation, for data storage, for really bringing in that whole digital and information era all together with what's going on in biology. Again, I've started up 5 new projects in a number of areas. I've got some funding and put them up together where people are doing things like I mentioned earlier, putting protein on silicon. You know, trying to use DNA and RNA to store and transmit information, to do these kind of things. And we're not alone in this. I mean, believe me, a lot of other people around the world are thinking about this, how it might happen. But this, in the end, could be bigger than anything you could think of. I also like to think the final thing. I come to say often to people, you know, having been in robotics for 40 years, maybe we're never going to build an intelligent robot. Maybe instead we'll have to grow one. All right? And that's where biology could potentially go. And I perhaps should leave you the thing with you know, I think there is, you worry about AI regulation. Wait till you get to biology. What could possibly go wrong? Material science. There's a wonderful book out at the moment, I don't know how many people have read it, by Ed Conway called The Material World. And he talks about, it just came out last year, but he talks about basic stuff, salt, iron, various things like that. And it's fantastic. You know, he says, well, you see this salt, it's so pure, you can actually make it into this. This sand is so pure, we make it, it's the only sand in the world you can make into silicon chips. You know, and this is how we build it, and this is how the whole, you know, civilization is built on these kind of material properties. And it is amazing, the kinds of things that humanity has managed to do in the last 5,000 years with materials. You know, it's everything in some sense in our life. Cement, you name it, all these sorts of things. It is really astonishing. And yet, the whole materials world is changing. You know, genuinely, I used to go to my lab in, I was in, you know, aerospace and mechanical engineering at the University of Sydney. In fact, I still am. And we had a huge materials group, and literally they used to spend their time bending pieces of metal and reporting on how strong they were, okay? And I get that. But now it's nothing like that, you know? It's the things that you can build are just unbelievable. So people, you know, it started, I guess, with, a much better ability to image atomic structure at a very small scale and understand how atoms and individual structures operate and work with each other. And that resulted in new types of composites initially, and new types of alloys, but then moving on from that, these whole composite structures where you have these metamaterials of lots of different things, different types of materials, all working in close combination to achieve both a mechanical but also electrical or other properties and other kinds of devices. Really astonishing kinds of things that people are doing, which is so far beyond even what we were doing just 20 or 30 years ago. People talk about metamaterials. Again, perhaps a little story from defense. I can't go into too much detail, of course, or I'll have to kill you, but that's okay. You know, where we're building coatings for aircraft and missiles, you know, that deform at runtime. You know, so the thing changes shape so that things that are hitting it like radar signatures and laser signatures can all be deflected, absorbed, retransmitted and various things like that. And all of this is kind of programmable. So the whole material structure literally changes as you move. Those are the kinds of things that are not just people's heads now, they're genuinely coming out and happening. And then even weirder things. There's a great centre I reviewed down in Monash who are building what are called topological materials. Topological materials, you think of 2D and 3D, they're building 1D materials. Okay, I'll let you think about what a 1D material might look like, okay? But it turns out 1D things are much better at conductivity than 2D things because there's less atoms in the way. All right, and so they build new types of low energy semiconductors with what are called topological materials. And one of the big challenges, I was looking at the US Materials Academy of Science Materials group, is to really understand materials in different functional forms too. Materials, for example, that are not in steady state. So materials that are forever changing all the time. What properties does that give you? All out of our understanding, I guess, of the atomic structure of what's happening. Chemistry, new types of energy system, whole ranges of different stuff are possible. And again, I think this, we'll come to it a little bit later on, is kind of being driven a little bit by the fact that, you know, we have this compute power to do some of these things, and we have also the machinery and sensing to measure basically what we are doing. So materials is an area which is really fascinating as to what's going on in that area. Energy. As I said, I'm a net zero commissioner. What I slightly worry about, I hope there's nobody's recording this too much. Oh, do you record this? Oh dear. All right, okay. Maybe I won't give any names to things then. I do worry, I have to say, in general, without blaming anyone, that a lot of our policies in energy have very little engineering around them. In fact, there was an article in the Fin Review, I think last week, that basically said the biggest problem with our energy strategy is it's driven by politics and not by engineering. You know, there are enormous opportunities in this area. We often talk about the fact that Australia could become an energy superpower, various descriptions, and yet some basic things. Let me give you just one example, all right, hydrogen. Everyone says hydrogen is going to be the next fuel. It's going to be a wonderful thing. But have you ever looked at the physics of hydrogen? There's an issue about it having to be very, very cold, which makes things tricky when you're trying to build storage or transmit it or port it in any kind of way. But the other problem, of course, is the fact that, you know, its energy density is only a 1/12 of natural gas by volume. So if you want to ship it to Japan, you actually need 12 times as many ships, even if you could design the ships to ship it. All right, so it actually is not a very good energy system at all, other than the fact that we know about it and we use it and it goes into lots of other materials, like ammonia, for example. So, you know, a hydrogen strategy is probably less of a good thing than, let's say, an ammonia strategy or some other kind of chemistry strategy. And lots of people now are inventing different ways of doing it. And I will make a prediction at this point. I think actually the primary thing we'll use hydrogen for in this country is for manufacturing fuel. All right, and we will export fuel and gas in the same way that we currently export fuel and gas. And maybe what we'll do is to design better fuels and better gas, because we can now manipulate it at scale in that kind of way. At the same time, I think the things that are going on in the solar area, and this is another area where New South Wales has been fantastic, you know, in terms of its research at least, is the solar efficiency. We have a property up in the country, we're completely off grid, so we're just solar and batteries. And I think what's interesting there is, you know, I guess even only, you know, 8 years ago we bought solar panels, and when it got cloudy we ran out of power. Now when we buy solar panels, they work when it's cloud. It's completely different, all right? The technology is just amazing what's happening now. We can use it in so many different ways, and also the cost of them. I'm buying new solar panels at the moment. I can buy a 500-watt solar panel for $150, all right? I can't even ship it from Penrith for that, Okay? That's how cheap it is becoming when you're talking about energy generation. Our only problem with rolling out solar is the fact that we need to get planning permission to do it. So at the moment, I'm afraid, not one of our renewable energy zones has got planning permission. So we are a long way behind where we're going to need to be by 2030 at this point. At the same time, great new work in battery technology. There's new foundations of a whole different interesting areas of electrical engineering. Again, here is the problem that we're facing. We no longer have, a dozen odd power stations, with nice rotating generators. Rather, we've got 1 million people with solar panels on their roof who don't talk to each other, all right? So how do we build a coordinated grid? How do we control that grid? How do we get all the phases to be in sync? Otherwise, the whole thing goes down. Our biggest nightmare at the moment is not during the day when we've all got the aircon on. It's in the middle of the night when nobody's using any energy. What do we do with it? How do we coordinate it? How do we get it together? That's when we're going to begin to have blackouts, all right? So there are issues around whole new technologies, organisation, control and everything else that come along with energy. Lots of challenges, but I have to say Australia, in my view, is in a good position to genuinely drive an energy future. I think it works in so many different ways. And I need to put on the end here, I'll add on the end, nuclear power. Look, I often tell this story. I worked in the nuclear industry back in originally in the 1970s. 1979, I was a young student, right? I went into the advanced physics group at Rolls-Royce, who funded my degree. And the guy in the next office, he was in the office, I said, "What are you doing?" He said, "I'm designing an SMR for the civilian market." And we still don't have one. All right, that's how long it takes to get things done in the nuclear industry. It's not as easy as people think. And yet at the same time, I was reading, the World Fusion Report a couple of days ago. $20 billion has been invested in fusion startups, companies, all right? New companies doing new types of fusion reaction with light, with different types of tokamaks, with different types of pressure containment vessel. I have a strong suspicion we're going to get fusion energy before we're going to get a nuclear reactor in this country, to be honest. There's so much more interest and value going into it. So let us see. Taking it all together, I think the really interesting thing for engineering is at the intersection of all these disciplines. So I'm going to go back to, I'm going to really pull out, I guess, two areas. I want to talk about what I think of as computational design and what that's going to deliver. And I'm also going to pull out manufacturing. And really talk about how that might happen and try and understand what perhaps future industries might be in Australia on the back of that. So I think I've mentioned a few times, we have got to the point now where we have enough compute power to do virtually anything we want, and we've got enough storage for any data we want. I think the challenge at the moment is still bringing those two things together to do something useful other than create chatbots, okay? And by that I mean using them properly, for example, to control big processes, to monitor the environment, to manage big energy resources, to do these sorts of things. And I think the key to all of these things is trying to bring together algorithms and physics at the same None of these problems are that easy. I'll give you an example. Again, I think I mentioned earlier, I worked for Rio Tinto. One of the big things I've been interested in for a long time is how to change the way people do exploration. Okay, and exploration is a lot of data. Okay, you have electromagnetics, gravity, magnetotellurics, drill data, and all this kind of stuff. And yet, with all that data underground, and look at these maps around you, the world itself is immensely complicated, much more complicated than any amount of data you will ever gather. All right, and so people basically take this data, typically one at a time, and essentially use that data, which is often, if you think about it, like gravity data, is actually two-dimensional because you're measuring gravity just at points, right? And what you really want is a three-dimensional structure. You try and regularize it in some way so that you can kind of guess what's going on underneath based on your experience plus the data. And yet the new AI, new machine learning techniques now should allow you to combine all those data types to really bring in all the knowledge from every geologist and genuinely try and build the best possible model that you can of that geology, all right? And in that way, discover deeper resources, better ways of operating them, and all these things. That's the vision for what computing power and AI could be doing for areas like geology and mining and so on. And I think perhaps a good example here that's also worth going into detail is the work that was done by DeepMind developing AlphaFold. I think we've all heard of AlphaFold now, at least, right? But I think it has an interesting story, right? Because the algorithm itself was originally developed for playing games. And it's pretty much the same algorithm, right? They developed it originally for playing checkers, and then they developed it for Go, and it's called AlphaGo, if you remember. And I'll come back to how the algorithm works in a minute. And it was also set up by this guy, Dmitry, who basically, from age 12, wanted to play games on computers, right? And sometimes, you think, my child, that's all they want to do. Can't they do something else? Well, this guy won the Nobel Prize playing this sort of thing. And also, one of the games he entered, interestingly, was a protein folding game. He was 12 years old at the time, all right? What happened at the time is people didn't know how to do protein folding, so they kind of crowdsourced it. They gave it to lots of people, and they said, use your best thinking to try and come up with a good way of doing it. They gamified it, effectively, all right? So these two kind of pieces come together. So the way you solve Go is actually, it turns out to be much too hard to just use past Go experiences. You actually have to have a sense of strategy as well. So they have a thing called deep reinforcement learning, which is not deep learning. I'll just be careful here, right? Nor is it large language models or anything like that, right? What it really says is, well, strategy-wise, we think there's this bucket of stuff, and this bucket of stuff, and this bucket of stuff. And then within that bucket, the bucket is now small enough I can actually use physics and explore the space. And now I take that exploration of the space and combine it with some of the data, and I will end up with a much better guess for much, much harder problems than I could previously. So the big problem with Go is the solution space is just bigger than there are atoms in the universe, and protein folding is even bigger again, okay? And they took exactly the same idea, and this is AlphaGo, went to AlphaFold. And for a couple of years, they basically tried to figure out how to use data to come up with protein folding. And it turns out there isn't much data, right? There's only 150,000 known proteins that have been, used crystallography to basically understand the structure of those proteins, and they're in a big database. So it's not like a big data problem. Let's be careful here, right? It's not like it covers billions of proteins. It's only got these. And so they took that, and then they added some physics. They knew about how different types of parts of proteins rotated, how they folded, how they interacted with each other. And so once they'd got an area that said these proteins look like this in this area, then they basically applied physics to understanding how those proteins folded, and then they combined the two together. And it's an interesting process they used to basically take the data stuff and the physics stuff and put it together and come up with a solution. And let's be clear, the first time, not AlphaFold 1, but AlphaFold 2, because AlphaFold 1 didn't really work. AlphaFold 2, they took it out there, and they took it to protein fold inclusion, and it just blew everybody away, because this is a problem. And I remember people when I was, again, a young academic at Oxford, who were spending their entire lives trying to do protein folding and never really getting too far, right? They went in, and 97% of human proteins they managed to solve with an accuracy good enough that people knew what the structure was, all right? So you could use it, not perfectly, let's be clear, right? AlphaFold is not a perfect thing, to actually see what those structures of those proteins can actually be. And they again went on to use that, not just to do that, but to predict millions of proteins that don't even exist, okay? To design whole new proteins and systems, which are perfectly viable proteins, all right? It's just that our genomes don't produce them at the moment. So the opportunities for this are just like stunning, beyond belief. I mean, it's, you could almost, you could produce, I mean, in some sense at the moment it's a one-directional thing. You've got a bunch of proteins and you can produce them, but you don't necessarily know what they're going to do. Which brings me to AlphaFold 3. So AlphaFold 3 is genuinely engineering. It's now doing the opposite, right? It's basically saying, well, I want a protein to do this, okay? Maybe to dock onto a spike protein, maybe to design a particular mechanism that actually moves, so a little bit of a machine or something. What's the RNA that would produce that? And therefore, what's the DNA I need to construct with CRISPR and everything else to manufacture that protein? Right? That is really, really interesting. That is, I don't think people realize just how impactful that's going to be. Really being able to design these sorts of things in that way. It's still, I will have to point out, the beginning of the story, because most things that happen in biology are not do this and X will happen. It's do this and that and this network and combine this together and then this will happen, if you see what I mean. So we still are at the point where we need to bring all these different components together to make it happen. But in the end, that design, that digital design has been enabled all right, by the compute power, by the fact that it's a computer scientist who learnt biology. And actually earlier in the year I ran, up at Macquarie University, I ran a course called a Crash Course in Biology for Computer Scientists. How can we get computer scientists to talk about biology? Next month we're running one called a Crash Course on AI for Biologists. Okay, you get the picture. We really need to get these people together to compute. So I love this field. I really look at it and I'm astonished at what could potentially happen in these areas. And although I've talked a lot about biology, you name the field, materials design, what kind of ecosystem I want, everything else. These are the sorts of things that we really are going to happen in so many ways. I also think it's fair to say that compute power is going to come to help us as well. This is one area, and I find this is also very interesting, where quantum computing will help. All right, so quantum computing is not right for every problem, okay? But the idea where you're going to do that simulation of proteins moving around, atoms interacting and things like that, that's perfect for quantum computing. And so I think even with a relatively modest quantum computer, quantum simulation is really also going to really start to move this whole thing on. So let me say my last example, which is manufacturing. I try and have these conversations with my minister about manufacturing, because manufacturing, I have to be honest, is not about blokes bending pieces of metal anymore. In fact, no future manufacturing is going to look like that, even though that's actually what ministers want. Okay, they want employment, they want jobs, they want people, with overalls on doing manufacturing. Modern manufacturing is really interesting and different in so many ways, right? We are building an RNA manufacturing facility up at Macquarie Park, okay? We are basically manufacturing RNA for not just vaccines, but therapeutics, for veterinary purposes, and if I have my way, for manufacturing proteins and structures and machines as well, okay? So that's manufacturing these days, and it's very different. It's about controlled, clean environments, but the value of what you're putting out at the end is huge. That's where the value add, in some sense, that we can do. At the same time, out at Bradfield, we do have an advanced manufacturing research centre that opened 2 months ago, and you look at it, it's amazing. I don't know, I mean, if you ever seen, people have heard of them, but these new additive manufacturing machines where these metamaterials I've been talking about, these machines can make structures with all these different materials all linked together in different combinations with different structures. You program it, you design it, you simulate it on a machine, you press a button and it manufactures it. Additive, it's a whole range of different stuff they're doing. But that's just the beginning of it. The next door building will be the semiconductor packaging facility. So again, you might think, what? New South Wales doing semiconductors? Actually, the value in semiconductors, and this is manufacturing these days, is not in making them. The biggest companies in the world make nothing. NVIDIA makes nothing. It designs really, really, really good designs, and it sells and uses chips, but Taiwan manufactures them. Equally, your Apple iPhone, it's not made by Apple. It's made by someone in China and now India, okay? These sorts of things are happening, and where you really make the product is how you put it all together into the system. That's why we're building a packaging facility. Unbelievably, there are 100 companies, more than 100 companies in New South Wales in the semiconductor industry. All right? And in fact, we are the world leaders, believe it or not, in the design of semiconductors for communication systems. Big companies like Broadcom, trillion-dollar US company, do their communications design here in Sydney. Okay? So these are the sorts of areas where, again, manufacturing is changing. So manufacturing is now becoming, I would say, very bespoke. People design and build one-offs or two-offs or 10-offs. It's also becoming very diverse, the materials. It's becoming biological. Of course, people will have heard of Vow Foods as well, and they manufacture synthetic food using cell cultures, right? They manufacture meat, effectively, and various other things. These are not vegetable replacements. These are actual cells that have been cultured to look like meat, taste like meat, and be meat, if you see what I mean. So that's a new manufacturing process. Like I said, in the semiconductor sector, it's about design, it's about integration, it's about building new products. We do medical devices here, but the bottom line is it's a lot of it, we're really good at medical devices, but we tend to design and make a product out of them, and that, if you like, is the value add that goes along with it. So there's a huge opportunity for really looking at how we do manufacturing here. I worry a little bit when this government says we're going to manufacture batteries or we're going to manufacture solar cells, right? I mean, I just repeat, I can buy them for $150, all right? A little vat of RNA is worth $1 million. Which one are we going to make, okay? So I do think the opportunities are all there. We have enormous skill sets in all these different areas here. And we have, if you like, the opportunity in lots of different ways to really make manufacturing different in this state and in this country, of course, and competitive on a global sort of thing. What's our main market in this area? So again, when I talk to engineers and I talk to engineering, people who are students who want to become engineers, I try and tell them that's the future. Do biology. That's going to be engineering. That's the sort of industry that's out there. And you look at places like Macquarie Park. Did you know that there's a company up there, the world's biggest designer of yeast? Okay? It is a real expert in designing yeast. And the yeast is used for making fuels, for reducing waste, for reclaiming land, for doing a whole variety of things. It's those sorts of jobs and those sorts of things that are really going to be fantastic. So industries. I think Australia has enormous opportunity. I think based on our comparative advantages, we are always going to be big in agriculture. We've got a lot of land, we've got a lot of very clever farmers, but I have to say when you start combining it with biology, with digital, with all the things, we are a lead in this state and in this city, in fact, in areas like agtech, using digital technologies for climate control, for managing plants, for managing weeds, for doing robotic agriculture, all these things. This is a kind of huge sector that we're in. Medical devices, I've been chairing the Medical Devices Fund since for the last 6 years. There are enormous changes coming in applying all these areas. I also think minerals and mining. People say, no, that's the thing of the past. Actually, it's not at all. There's this big bit in Australia, which you probably have noticed on maps is coloured yellow, between Sydney and Western Australia. Okay, the bottom line is no one really knows what's there at all. Okay, and there's a wonderful project that's been going now for a decade called the Uncover Project, which is really trying to bring together data and machine learning techniques to understand what's beneath the surface and use that, and that will be, but the materials will ultimately underpin our future. So I think we can build on those technologies in different sort of ways and have ourselves a niche in automation, in machine learning, in doing these things well, and we can lead the globe in basically doing that. So these are the industries that I think the new engineering and the new technologies will drive. I'm going to end here actually, but I wanted to end in an interesting way with a fairly long quote, if you don't mind. It's a little bit, not negative, I wouldn't say, but a little bit threatening, okay, the quote. But I think it kind of summarizes some of the feelings that I have. I feel like a young engineer again sometimes with these things. And it's by this guy, this Israeli philosopher, writer called Yuval Noah Harari. I think many of you have probably seen his books, Sapien and things like that. But this one really hit me and underpins it, I think. In the early 21st century, the train of progress is again pulling out of the station. And this will probably be the last train ever to leave the station called Homo sapiens. Those who miss this train will never get a second chance. In order to get a seat on it, you need to understand 21st century technology, and in particular, the powers of biotechnology and computer algorithms. These powers are far more potent than steam and telegraph, and they will not be used merely for the production of food, textiles, vehicles, and weapons. The main products of the 21st century will be bodies, brains, and minds. And the gap between those who know how to engineer bodies and brains will be bigger than the gap between sapiens and Neanderthals. In the 21st century, those who ride the train of progress will acquire the abilities of creation and destruction, while those left behind will face extinction. Thank you.
Because here we have this extraordinary range of optimism and excitement and everything that's happening. First of all, other people's questions. We're caught in a very bright light there. Does anybody want to start, or shall I start?
Go for it.
I don't have questions.
No.
Your thoughts on growing structures?
Yeah.
To me, it appears to be an obvious thing to be able to grow.
I agree with you.
Smart structures.
I agree with you. I mean, I have a few projects I've tried to seed that are basically doing this, and it makes sense. We are a protein structure ourselves, right? And, we ought to be able to use that in interesting ways. And I think there are promising signs that people will do that. I think one of the biggest issues in an engineering sense will be how to scale it, if you see what I mean. So, there's always this, in the end, you'd like to grow structures that really have the strength and versatility of, I hate to say it, but things like timber, and that sort of property. But really making it self-repair, being able to integrate, being able to change, many of these other things. I do think that's on the horizon. There was a question just there.
Well, look, I've so many questions, Hugh. That's a phenomenal excursion around the place. One question is, you were saying that looking around this room, well, look, the question I want to ask you is, what do you believe? Do you believe in that we can actually go to the extent of creating a digital Earth? This is a phenomenon that Digital Earth Australia is subscribed to. Yes. It's a global society, international society for Digital Earth. But you were implying, or you said, that there's not enough capacity to do that with the data.
Not at all. There have been a lot of projects in this area. Glass Earth, I think, was a CSIRO project 20 years ago, right? I think the Uncover project, which is an Academy of Science run thing, has been going for at least a decade, as far as I'm aware. We have our own internal projects in Rio to do similar sorts of things. And let's be clear, you can create a glass Earth, a virtual Earth with not much data at all. It just won't be very right either, okay? But if you try and link everything together, not just the, data, look at the work that Geoscience Australia has in its databases, and you start adding all the data from the new satellites, like that company FLEET, which is doing, satellite-based sensing, but also combining it with passive acoustics, so really deep observation type of stuff. And, I was at a company on Monday looking at a quantum magnetometer, which will give you total perfect precision in magnetic fields. These sorts of things. These sorts of data, the problem is putting them all together will really give you a way of doing that. But let's be clear, there will never be enough data. So you do need to have these machine learning and algorithmic components that genuinely draw together and make an inference about what's under there, even in places where you can't see. And we're not unused to that. People try and figure out what's in the Earth's core based on what they see on the surface and so on. And those are estimations and models and physics, which basically allows them to do that. So we're not afraid of doing that at all.
Don Hector.
The future you've sketched out really is highly dependent on having a very highly skilled workforce and a well-educated population.
Yep.
Australia's going backwards in international comparisons in STEM and other scientific and education generally. We're defunding universities, regardless of your political flavour. The left and right of politics are defunding universities. How are we going to meet the challenge? My first question is, how are we going to meet the challenge of providing the people who have got the necessary skills to do the things that you have described? And my second question is, what becomes of the people who just simply don't have the innate ability to engage with the sorts of things that you're describing?
That's why I used the quote at the end.
So
let me say two things. I think, yes, we're going backwards, but I have to say what's even more worrying is the rest of the world, in the Western world at least, are going backwards even quicker than we are. All right. So this is not an Australian problem. This is a problem where people get the opportunity to make free choices, and they look at doing something like this, and it looks hard, and it doesn't look terribly rewarding, if you don't mind me saying. And so it's easier to go and do something else. Right, and people do become a lawyer, become a doctor, whatever else. It must apologise to all the lawyers in the room. Can't leave an evening, and so I apologise. All right, okay. So how do we change that? And I think we're not very good at doing that in lots of different ways. And it starts, frankly, with parents who, I've got a smart kid, and and what do? Do they apply for biology? No, they apply for medicine. Do they apply for thing? And that's the problem in the end. Okay, so we don't. No, you can't. Just hold it there a second. So that's part of the problem, right? The other part is we are our own worst enemies, all right? I am an academic and a technologist and everything else, but to be honest, I'm not sure I would fund universities at this point, all right? When you look at the kinds of educational experience that engineers are getting, and scientists are getting, and everything else, it really is not at the level it needs to be. okay? And universities, I mean, I went through this in the UK. I mean, I went and protested against Margaret Thatcher and everything else, all right? But at the dip, everything slightly changed, right? The chief scientist and the ministers got together and said, we've got to stop this. And they did something and it really worked. And we have to get to that point in this country where universities, you know, have got to realize they've got to do something for the country, not just for themselves, all right? And they genuinely have to start thinking how we are going to deliver to people like this and not a lot of the other things that they tend to worry about. You know, I often say, Sally and I, well, where's the compulsory course for everyone in this group in statistics rather than the compulsory course on something else that we're not interested in? You know, and that's the problem we have to face. All right, so we are to blame for this ourselves, universities, parents, everybody, and the government itself will sit up and notice when we show what we can deliver.
Can I then just push on that one, because where you say energy policy is being made without any engineering. How can we get these issues and these possibilities into the public discourse? How do we, I mean, that is one of our problems as a society. What we're wanting to do is to get them into the public discourse so that, and look, they're hard enough to understand even when you do it, this marvellously clear explanation, but mostly trying to read some of this stuff can be quite, I can read Yuval Harari, but I'm not sure I'm too good on the quantum mechanics.
Yeah, look, I would agree with you. I mean, energy is an existential thing at the moment, in my view. You know, we have to get this right. And it's one thing I really worry about is the fact that we won't get it right, and as a consequence, we will do things we really shouldn't be doing, if you see what I mean.
But how can we change?
So how do we do that? Look, that is tricky. I mean, I have to say here, you know, I will say we have an exceptionally good energy minister who does listen and does change things, right? And I think some of that is because we've developed a level of trust between what I think is the community and the minister who actually is not an energy specialist, you know, and so on. And then as a consequence, she will listen and take advice in a good way, if you see what I mean. I think for some reason that's been lost in the federal government, right? There's this thing about being able to take honest and truthful scientific advice, all right? And while I genuinely think it does happen here in New South Wales, I'm not so convinced that it happens at the federal government level. And to some degree, that's the sort of thing that needs to change. So you're asking me a question that says, well, how do we change politics?
It's not just politics. I mean, you referred to parents.
Yes.
How do we change the public discourse? How do we make a space to create the interest in these things? I mean, if we think back to the origins of our Royal Society, and that period where the Quakers of England, you know, created this complete new way of thinking and doing, and the Royal Society was so powerful. It wasn't, you know, tight like our learned academies talking about one thing. It was broad debate.
So the answer is I think the Royal Society may well have a role in this, right? I mean, my experiences of the Royal Society in London, right, are that they have members of the society embedded in government. Members who genuinely work properly with the government, and that makes the trust in science much, much higher in general. And they have chief scientists in defence, but not just in defence, in the business one, in the health area. They have a lot of chief scientists, you know, who genuinely work very closely with government. And that's probably the sort of thing that needs to happen.
Anyway, Susan.
One of the other things for all four, and especially as they come together, all the four areas you talked about, will be computing power, server farms, which will consume more and more energy and will need to be themselves dramatically transformed to be able to deliver on the promise. So talk to us about that, particularly in New South Wales.
I'm a little surprised that it's come this way. I mean, for me, an interesting thing was, everyone's using these big, large language models that are taking up the power of a couple of nuclear reactors and so on. And then the Chinese came along and did it for, 20th of the power and a 20th of the cost. And then actually 3 days later, I don't know whether everyone followed it, but then there was another group at Stanford who produced the same result for, 100th of that. So actually, a lot of it is people need to figure out what they're doing and how they're doing it, and I think that will move things on. At the same time, there are technologies coming which will enable data centers to use much less power. So not just smaller chips, but for a simple one. There's an interesting company even in Australia that actually cools its chips with a fluid, and consequently is able to sort of halve the power consumption of what goes on in a data center. So that kind of thing. There is Albert Zamoya, I think it is, at the University of Sydney, has spent his research career on developing low power algorithms. That is, algorithms that operate efficiently on a data center that use much, much less power, and these sorts of things. So when we hit those constraints, those sort of things will change. And again, in the, I like to think of it, in the semiconductor area, I'm astonished at some of the things that go on in this area, right? Because you used to have this very, very expensive chip, and then next year it's not expensive and you've got this, not a chip, but a wafer now that's this size. Do you know what I mean? And it's doing this. And, the ARM chip that you've got in there, in that phone, which only came out last year, right? It's built with 3 nanometer technology. And it can do what a data center could do only 3 years ago. And it's on your phone. So I think things change, all right? And also, according to my projection, we're not going to be doing large language models after next year anyway. So.
Okay, let's go to the next question, yes.
Yeah, hi Hugh. Noel Cressy from University.
Hi Noel, how are you?
I'm well, thank you. Thank you for your engaging talk. Could you say something about social engineering, please?
Yes.
The good, the bad,
well,
and even the ugly.
Well, you're sitting next to the expert, right? Look, I think if it's one area I've not talked about, because I'm an engineer, I guess, and I'm thinking about technology, it's the fact that there's many good things that you can do with this technology that genuinely will help society in different ways, right? So, again, Sally's more the expert than I am, but using data and using algorithms to predict outcomes from social interventions to genuinely better manage a lot of these things that go on. And again, this is an area where perhaps we could do an awful lot better, because you look at the budget, we spend most of our budget not on defense and energy, but on social engineering in different kinds of ways. And so being able to even have a small impact in that area would have enormous outcomes. So the types of algorithms, the types of approach I think in that area are important, but also social engineering, if I might say, in areas like energy. Renewable energies do have a real opportunity to lower energy costs. They don't at the moment, but they will do, and they should and they will do. Again, I come back to the thing that solar power now, solar panels are so cheap, they're not even worth a couple of bottles of wine. You can buy solar panels, that sort of thing. Okay, you need batteries still and everything else, but the ability to use that and transform social outcomes, give people energy, at least at certain times of the day, if not forever, is amazing. Those sorts of things that are going to go on. And equally in the biology area, again, there are opportunities for really making these things much more accessible, much more useful for many more people. At first I was very alarmed, although I'm a little bit more comforted now. You can, of course, go out and buy kits on the internet to design your own bacteria now. Have you ever tried this, guys? With gene editing and CRISPR technology and things like that. And again, you've got to think what could possibly go wrong. But there are now school competitions where school kids are figuring out, here is a toxic waste dump. I'm going to design some bacteria to eat that toxic waste dump, and they do. It's a really amazing thing. So I think the bar coming down and the ability for everyone to use these things is also going to be interesting from a social point of view. And it's interesting, the media don't focus on that, right? It's all about social media. It's all about negativities and everything else, whereas there are so many positivities about what this technology and what these sort of things can do. Yeah.
Okay, we've got Robert Marks, then we've got at the back again, and then 3, 4. And that'll have to be it, I think, because we absolutely have to leave on time, or we get charged a fortune by the library.
Thanks, Hugh. That was a fascinating talk. I was once an engineer, but I haven't for many years. But I wanted to ask you about the limits of design, that occur with emergent properties. And that is to say that you don't know what you're going to get until you actually build it.
I couldn't agree with you more. So again,
an example of that is designing chemicals which are blue in colour. Very simple, right? But we can't do it at the moment.
Yep.
We have to make the chemical and then see what colour it is.
I think that particularly is changing. But I mean, you're absolutely right. My first experience of this, and this shows you how long ago it was again in the advanced physics group at Rolls-Royce, and one day a huge box of cards arrived, computer cards, right? Some of you may not know what they are, but sort of thing. And I said, "Oh, what's that?" Sonny, I was told they're called correction factors. That's the answer we want divided by the answer we've got. So they knew what they wanted, right? And they had to put it there. And it's true everywhere. Any sufficiently complex engineering system, you have to kind of make it to see what happens. Not just nuclear power, but for example, I mean, people really don't know quite why aeroplanes fly, right? You try and move the engines around and they stop working, all right, or anything like that. The reason that an A380 looks a little bit like a 707 is because that works, right? It is still hard to do that kind of thing. Biology is even harder. It's ambiguous, it's multi-connected, it's got so many things, and yet people have the computational tools now to begin asking those questions. And I think that will change things. I genuinely do, in an engineering sense.
Where was the next one? And then 3, and then there was one there. 4. Okay.
The nexus between...
No, sorry, we're going to the one at the back, and then stand up.
Thank you. Thank you for a fantastic presentation. My question is probably a day-to-day application of engineering and energy into the future, maybe in the next 10 years. With more and more people living to strata apartment, and people talking about, particularly in New South Wales, something over the next 10 years, the gas prices will actually going up. So they're actually rushing to changing gas into electricity. So therefore they're spending money on now thinking investing in something to converting the gas facility into the electricity, so therefore the cost will be cheaper. So with all the energy or the development in this area, in terms of the mix, what do you think about in 10 years' time, where the gas market coming back, or the electricity will still be in the go, or the battery for the strata living?
Okay, it's a very complex, so the answer is pretty complex, so I'm going to try and make it simple, right? I think gas is going to be an important part of the transition going forwards, okay? Because, even with our system fully off-grid in the country, we've been running it for 7 years. 1 week last year, was it? We nearly ran out of power because it was really, really overcast. And that's when you need gas. Do you see what I mean? So no matter what you do, you can't rely, it's hard to rely just on one kind of thing. And so gas, at least, is going to be part of the transition, in my view, for the near future. By near, I mean next 10 to 20 years. And that will enable the transition and make it, I think, easier for the renewables to come online. I think we're being a little premature trying to remove gas, from the mix. And I do think that in the next couple of months, you'll see a big change in the attitude of politicians towards gas, because it's suddenly dawning on them what's happening.
Okay, and yes.
The nexus between academic R&D and commercialisation, and I want to lean on one of your areas of medical devices. We've been speaking for too long about the Cochlears and ResMeds and their 30-year-old stories. How do we deal with creating the next 100 or 50 world-class Australian inventions, commercialised at known global markets? What do you see as the...
So that I think so let me be careful here. There are several stages to that, right? There's the startup to something that can be commercially invested. And I have to say, I think we've got that sorted. So I've been chairing the Medical Devices Fund. We give out investment to about 5 companies a year. Not enough, maybe. But in the end, those have gone on to raise $2 billion. And there have been a lot of really great startups, some of them now valued over $1 billion. Elastogen, that breathing one, which listed on the stock exchange 2 years ago. So a variety. So that kind of thing happens. We've extended that. We have the Physical Sciences Fund. We have the Biosciences Fund. We have the Quantum Computing Fund. We have ... And all of them are really amazing. So they get companies from an academic lab to the point where someone will invest in them. And that's has in the past been the missing link. But I think that we may not have it enough scale, but it's certainly happening. It's happening in big time in New South Wales. We just released the innovation blueprint last night, you know, and 65% of all startups are happening here, and they're all in these areas, right? What we are not yet very good at is scaling. So getting from the point where you've got that company and you then want to take it into the big billion-dollar kind of category, and that's the big scale-up. And for all the MDF success, it's not been very good at that. Okay, so when companies get to a point, again, I'll use Elastogen, there's a couple of others as well, they get bought. And the next time you see them, they're based in Milwaukee. And then we've lost it. Do you see what I mean? So we have to work on how we actually scale things now. And I think that's doing something like the RNA facility is a good example. There's a reason for them to stay here and be here, because there is no other such facility anywhere. All right, and then you get the talent, you get the companies moving in and everything else, and you need to make that kind of thing happen. Medical devices, you know, the one thing we do have is a really good talent pool because of Cochlear and ResMed and people like that, and we have managed to retain some of those companies. The other thing is we got some really, we got investors who understand the area in a global sense and are capable of attracting good investment and so on, and so make it happen. So it's not a finished story, don't get me wrong, but that initial step, I think, is the transition from academia, despite what people say, into companies is roaring ahead.
Tibor.
Thanks, Hugh. Tibor Molnar, Sydney University. You paint a very interesting picture of the future for the next 40 years. Everything's going to change, everything will be upside down, It's all going to be terrific and fantastic. And I admire and share your enthusiasm for that next 40 years. But of course, everything we do has unintended consequences. So what I'd like to ask you is to probe a little bit into the things that keep you up at night. What are the risks? Where are the hurdles? Where is it going to go wrong? What are the problems that worry you about the possible implementation of the next fun things that we get for the 40 years? Where are the dangers?
What's the saying? You know, it's not guns that kill people, it's people that kill people. I think, you know, there's nothing wrong with the technology, but it's the way people are going to use it or use it badly, I think, that really worry me. You look at robotics, you look at the drone warfare that's going on in the Ukraine and things like that. I mean, you know, I was warning the British government about this, you know, close to a decade ago. We have to stop buying tanks. We have to start buying robots, you know, because that's what it's going to look like into the future. Synthetic biology, all the biological things, I mean, as I said, it does keep me up at night, you know. I mean, there are so many things that are possible that people will find bad things to do with the possible. Absolutely, you know. I mean, we had, again, I hate to go back to the defence thing, but we had a big biological warfare division, right? You know, which used to worry about smallpox and things like that. That's nothing in comparison to synthetically engineered viruses and things like that that go on. In fact, so much to the point they stopped looking at particular types of things and had whole areas that said, actually, we shouldn't try and build a counterpoint to smallpox. We should be ready to push back on anything we get. You know, so that Russian poisoning that happened when I was in the UK, that's a good example of how they managed to counteract that, given only a day's notice. Do you see what I mean? So there is a kind of thing. So there's lots of bad things that can happen. Don't get me wrong, and throughout history, we've always managed to turn many good things into bad things. But what I also want to point out to you is sometimes we're too negative. You know, I think, you know, all we hear about is the bad things about AI. Actually, there are many wonderful things that are going on with AI that are really great and fantastic and everything else. If only you over there would pick your head out of your smartphone and take a look, you know?
There's a note on which we must finish, and I want to thank Hugh very, very much. As a society, we're accustomed to hear from experts in their areas of knowledge. We've got elegant speakers, well thought through pleas, but what we've had tonight is a tour de force, worthy of the broad aims of the original society, looking forward, crossing intellectual boundaries, and doing so with scarcely a note. It was a very exciting overview with lots of provocative questions, and not just for scientists, for those of us who don't yet quite get what a one-dimensional material might be, or these issues of biology for data storage, growing intelligent robots, the metamaterials and planes which will be virtually invisible to radar. It's a fascinating space, very, very fascinating, but at the same time, as you've said, you've outstanding optimism. which I find incredibly admirable, but I rather like Tibor and possibly like Hugh Price here, who was involved in the Centre for Existential Risk, one does worry. So it's fantastic to have this sense of enthusiasm. And I think what is really exciting is that vision for New South Wales that you have, which is very, very exciting. There's plenty more that I could say, but I think really we should just thank our speaker for a tour de force.